Welcome to This Explainer. Today, we are taking a really enthusiastic dive into the fascinating physics of why our eyes sometimes fail us and exactly how we fix them. We're basically bridging the gap between biology and optical physics here. We'll be looking at the structural limits of the human eye and the incredibly elegant solutions that allow us to rewrite those physical boundaries. You see, the mechanics behind human vision are incredibly precise, but when that precision falters, well, the physics we use to correct it is absolutely brilliant. Let's kick things off with a classic real-world mystery. Picture this. You're sitting way at the back of a large lecture hall. Why is it that you can look down, scan your notes, and read the tiny, densely packed print perfectly, but the moment you shift your gaze upward, the large writing on the blackboard is just a completely blurry mess? You might find yourself squinting, straining, trying to force your eyes to resolve the blur. So what is actually happening inside the hardware of your eye in that exact, frustrating moment? This localized loss of detail is the core symptom of the biological mystery we are unpacking today. The culprit here is myopia. You probably know it more commonly as short-sightedness or nearsightedness. As the name suggests, near objects remain perfectly clear, but far objects become this dispersed, fuzzy mess. Now, to think like a physicist here, we really need to be mathematically precise about what's changing. A healthy human eye actually has a far point at infinity. Technically, our optical hardware is built to focus on objects extremely far away, like the distant stars in the night sky. But for a myopic eye, that physical far point has effectively shifted. Its optical hardware has essentially reset its own physical boundaries. The far point is now much closer than infinity, which effectively locks the viewer inside a localized bubble of clarity. If an object sits beyond this newly shortened far point, the eye just literally lacks the mechanical ability to focus on it.
So, let's get into the anatomy of a blur, the 3 causes of myopia.
Okay, let's walk through this biological chain reaction step by step to see where the system breaks down. Our eyes focus using these tiny, incredible structures called ciliary muscles, which actually pull on the lens to change its shape. When we look at something close up, these muscles work really hard to make the lens thick. When we look far away, they're supposed to relax, stretching the lens out thin. But in myopia, step 1, these ciliary muscles become fatigued. Think of it like holding a heavy dumbbell in a bicep curl for way too long. Eventually, the muscle just cramps up and utterly refuses to relax. Step 2, because they won't relax, the eye's lens cannot pull thinner. It remains locked in a state that is just too thick and too curved. Which leads us straight to step 3. A thick lens bends light very sharply, so it maintains an intensely high converging power and a dangerously short focal length.
So we're basically looking at a trifecta of structural issues causing this optical failure. First, there's that high converging power because the lens is physically too thick. Second, there's the ciliary muscle fatigue, where the muscles fundamentally fail to relax and release their tension. But there's a third major, entirely structural culprit we need to mention: an elongated eyeball. Sometimes the muscles and the lens are actually working perfectly fine, but the physical casing of the eye itself has grown just a millimeter or two too long from front to back. In a system that relies on absolute microscopic precision, even a single millimeter of elongation throws the whole focusing mechanism into complete chaos.
And here is the absolutely crucial physical result of all these causes. For far objects, the incoming light rays are bent entirely too aggressively. They converge way too early. You see, the retina at the back of our eye is this highly sensitive precision screen. But instead of landing perfectly on that screen, the image forms in the fluid, literally in empty space in front of the retina. By the time those light rays actually travel the rest of the way to hit the back of the eye, they've already crossed paths and started to spread out again. So the retina is just left receiving a heavily dispersed, noisy signal, creating that infamous, frustrating blur.
Which brings us to the physics solution. Enter the concave lens. Let's think this through together, looking at it purely as an engineering challenge. If the myopic eye has too much converging power and it pinches those light rays together far too early, what exactly do we need to do to push that image backward so it lands flush onto the retina? I mean, we obviously can't reach in and physically squash the eyeball back to its proper length, right? Nor can we easily swap out the eye's hardware. So we have to manipulate the light before it ever even enters the system. We need a tool that does the exact opposite of converging. We need something that actively spreads the light out. Enter the absolute hero of our story, the concave lens. This piece of precision curved glass or plastic acts as a diverging lens. Geometrically, it's thinner right in the very middle and thicker out at the edges. Because of that specific physical shape, when parallel light rays from a distant object hit it, the lens forces them to fan outward first. It gives those incoming light rays a much wider starting stance before they ever encounter the overpowered, overly curved lens of the flawed human eye.
And wow, this is where the pure elegance of the physics really comes into play. The concave lens is basically creating this magnificent optical illusion. Because it fans the light outward, it essentially takes the faraway object and forms a virtual image of it at a much closer distance. And where exactly does it place this illusion? Right at the myopic eye's actual far point. The brain has absolutely no idea the light has been manipulated. It just happily processes the virtual image that the concave lens has conveniently placed directly inside that localized bubble of clarity, working seamlessly around the broken biological limits.
When you place the uncorrected eye next to the corrected eye, the magic becomes so obvious. Without the lens, the light comes in straight, bends entirely too hard, and the image falls short, forming right in the fluid in front of the retina. But with the lens, the light is spread out first. The overpowered eye lens tries to bend it sharply, but because the light started out on a wider trajectory, the net converging power is perfectly reduced. The light rays now stretch just far enough to land precisely, perfectly on the retina screen. The noisy signal is resolved and clear vision is completely restored. It's a real game changer. Now, for those of you who appreciate the underlying math, the code of these solutions, here is the exact calculation required to bridge the gap between infinity and the eye's biological limitation. Your u, the object distance, sits at -infinity. That represents the faraway text on the blackboard. Your v, the image distance, is the myopic far point. We aren't just solving a random math problem here. We are calculating the exact, bespoke diverging power needed to take the infinite world and virtually project it right up to the boundary of what that specific eye can biologically handle.
All right, time for the quick-fire physics review.
Let's recap the journey of these light rays to really cement these mechanics. First question, when the biological hardware fails and the lens bends the light too aggressively, where exactly does the image actually land in an uncorrected myopic eye? In front of the retina. The primary spatial physics error of this condition is that the light converges in the empty space of the eye before it can ever reach the high-definition screen at the back.
Okay, moving to the biological culprits. Which specific muscles in the eye experience fatigue, cramping up, and failing to relax, which ends up trapping the lens in a thick, highly curved shape? Yep, it's the ciliary muscles. Myopia is frequently a structural issue, rooted in these tiny, hardworking muscles being stuck in an overly contracted, exhausted state, just pulling constantly on the lens. Finally, let's lock in our ultimate engineering solution. What exact type of optical tool do we use to fix this biological defect by actively diverging the incoming light? A concave lens. Thinner in the middle, thicker on the edges. It fans the light rays out, giving the overpowered eye the exact optical offset it needs to land the image squarely on the retina. Before we wrap up this explainer, I want to leave you with a quick visualization challenge. To truly cement this elegantly simple physics hack in your mind, grab a piece of paper later and sketch out the ray diagrams yourself. Draw the uncorrected, myopic eye viewing a distant object, making sure those light rays cross and disperse before they hit the retina. Then draw the second diagram, insert that concave lens, show the light fanning outward first, and watch the focal point stretch to land perfectly on the back of the eye. Mapping this out manually is honestly the best way to internalize how these mechanics perfectly interlock. We've taken a deep dive today into the precise mechanics of how we perceive the world, and how brilliant optical engineering steps in when our biology falls short. So I'll leave you with this final thought. The next time you look at the glasses sitting on someone's face, will you just see glass? Or will you see physics, literally bending light to perfectly rewrite biological limits?